I've put up there again the URL to the directory where I'm putting all the example source files from my lectures, but I'm putting them there after the lecture is over. So what you'll find there now is the code from Saturday. And today I'm going to talk about inductive relations and how to do induction on them. Before I go there, are there any questions left over from last time anyone wants to ask? All right, so I'm going to introduce how we work with relations, especially relations defined inductively in Calc. And I'm going to be using state machines for software as a running example. And the first example I'm going to use is the factorial function. Of course, it's a legal requirement that every functional programming related tutorial uses factorial somewhere. So I'm discharging that obligation now. And so here's the classic, straightforward, recursive functional definition of factorial, where we take in a natural number n, and if it's 0, the answer is 1. And if it's a successor of a number, remember s is basically the plus 1 constructor, then we call factorial on the number that's one smaller than the current one and multiply that result by the current number. So this is the recursive characterization of factorial, but of course we know if we evaluate this directly, this is not a tail recursive definition, so we might use more stack space than we'd like to. We might overflow some hard limit on how much stack space is available. So it's common to write a tail recursive version, and I'm going to formulate that as a state machine instead of just writing it as another functional program, just as a simple example of working with state machines that we formulate relationally instead of in a way that we can execute directly. So here's my simple state machine. We're going to have two kinds of states. One that I'm going to call with accumulator that has two parameters inside it. So think of this as, well, it's going to be a constructor of a data type, but you can also think of it sort of like a class or a struct that has these two fields inside it. The meaning is that n corresponds to the parameter n there, which is going to count down from some value to 0, and ac stands for an accumulator that we're going to keep multiplying into as we go along. And the start state of this state machine is going to be where the accumulator is 1. So when we want to start executing, we begin in this state where n is equal to the actual input n, and the accumulator is equal to 1. And then we're also going to have another state called answer is that has just one argument, which is the result of the computation. And whenever we notice that n equals 0, we can step over into answer is. And when n is not 0, which we can write as n happens to be what we get by adding 1 to some other number n prime, then we can multiply the accumulator by n, not n prime, and then we can replace n with n prime. And finally, we can say that this answer is state is a final state of the machine, and so when we get there, we know we're done, and the result of the computation is exactly the accumulator value stored here. So this is one of the most trivial state machines you could define, but hopefully you agree that it unambiguously describes how to compute factorial without using any extra state beyond basically the two variables encoded inside of the with ac state. So let's see how we can code that inside of Calc using inductive definitions. The first thing I'm going to do is define this type of states, which includes a constructor for answer is and a constructor for with accumulator, which I wrote in a slightly longer form here. And just like the data types we saw last time, each of these constructors has some arguments, and the answer is constructor takes a natural number as its argument. With accumulator takes two natural numbers. And I'm defining a number of relations over this state type. Each of these, or at least this initial relation, is parameterized on what is the original input whose factorial we're trying to calculate. That's this parameter here. It's written just like in the syntax Peter showed for AGDA, where some parameters of inductive data types are written so-called before the colon, and then they're automatically bound as parameters for all of the constructors. And what we're doing here is defining a relation that says that the initial states of the machine are exactly those that are with accumulator states, whose arguments are the original input and 1, which is what we want the starting accumulator to be. And we define another relation for what are the final states, which are exactly the states built with answer is. And the most interesting part is this step relation, which I'll write in more traditional inference rule style on the board. So if we're in a with accumulator state and the n part has been reduced to 0, I'll abbreviate these names actually to make it easier to fit, then we can take a step to the answer state. So I'm writing a right arrow here as an infix operator for one step of the system. So this inference rule says whenever we have n equals 0 in the with accumulator state, we can step to a state where we know that the answer is exactly the accumulator. And whenever we're in with accumulator where n is not 0, then we can take a step where we reduce n by 1 and we multiply the accumulator by the current value. So neither of these rules has any premises. They're particularly straightforward. And we can write them as inductive type definitions in Calc. One key thing here different from the definitions I showed you last time is that in this position where I was writing set before, I'm writing prop for the universe of mathematical propositions. These are meant to stand for kind of theorem statements instead of types of programs that you run. And I'm also writing some extra, the type isn't just prop, it's actually the type of a relation or a function to prop, where in the case of the step relation, we have two states, the start state and the initial state. And you can think of it as this is the function that, given two states, returns you the proposition that stands for it's possible to step from the first one to the second one. So here's the step from with accumulator with 0 to answer is, and here's the step from with accumulator with non-0 to a change to the arguments to with accumulator. Any questions about what this means before I start proving things? Yeah? The first line says we're defining a thing of type fact state, arrow prop. In other words, a binary relation over prop, or a function from a pair of appropriately typed things to the proposition that tells us whether this relation holds of those two things. Any other questions? All right, so let's process all these in Calc. So we've defined three relations, one corresponding to this arrow here telling us where to start, another corresponding to this convention of where the boxes are telling us when we're done, and another corresponding to the arrows I've drawn within the states of this system. They're not keywords, they're constructor names, just like before. We're just defining a different kind of data type that lives in prop instead of set. Right here. This is defining them. Just like we're defining, say, 0 and successor in the definition of the natural numbers. All right, so let's try to prove that this state machine, when it finishes, always contains the correct answer. And we can do that by defining an invariant that is going to hold of every state of the system. It will be parameterized over the original input, which is a natural number, and it will also take as argument one state of this machine, which is corresponding to those boxes there, and it will return a proposition that is going to be true at every point during execution, and which also implies that the answer is correct if we get to a final state. I've just filled in true here as the invariant, which is not actually going to be strong enough. So maybe we can come up with something better. Let me make some space here. I will be proving facts like these about it eventually, but I wonder if anyone has any thoughts on what would be a good invariant for this system. It needs to hold of every starting state. in every final state, it needs to imply the answer is correct, and it needs to be preserved by every arrow in the diagram. Yeah?
You could prove that the ending fact state is the same as what would be called factorial functions, commonly original.
Sounds like a good idea. So we can do that by, it sounds like you're describing a rule that applies for the answer is state. And you're saying that accumulator stored in there had better equal factorial of the original input. Yeah, okay. And we also want, that is half of the answer. Let's try to get the other half too. We have some accumulator like so. What would we like to say in that condition? Yeah.
The factorial of the original input should be equal to the factorial of n times the accumulator.
Yep, that sounds right. Let me give that its own line. Equals the factorial of n times the accumulator. All right. This looks very promising. Any questions or objections before we proceed trying to prove things about this definition? Yeah.
So with your state diagram up there, you start with an n, you add 1 to the n each time, and then you terminate when n equals 0.
And n is actually going down by 1 each time. This is not an assignment equals. This is a kind of pattern matching equals.
Oh, okay.
Yeah. Well, think of it as a specification of fact that happens to be naturally written as a functional program instead of as a competing implementation, if that makes you feel better. All right, so let's prove that this is a correct invariant after first making sure the type checker likes it. It does, so that's good. And probably our lives will be easier if I just reorient this so that the order of operands agrees here. We write fact original input equals in both cases. And I could even move the equals outside of this pattern match if I wanted to, but I won't go that far here. All right, so let's prove, my Emacs is in a confused state. I will restart it. We're going to prove that the invariant we've defined holds of every initial state of the system. We want to show that for every original input value, by the way, notice I have little for alls here, thanks to a tip from Clement about an extra library to include that displays some operators as Unicode symbols, and it will save us some space on the screen and make this easier to read. So for every original input and any state that is in the relation that says it is a correct initial state for the original input, we can conclude that the invariant holds of that state. And the basic way we're going to do this comes from the fact that this type fact init, this relation, is defined just like an algebraic data type, just like the data types we worked with last time in both Coq and Agda. And we can do case analysis on which constructor was used to build that value, just like we could for a natural number or a list. So I'm just going to run destruct, which is the general case analysis tactic. It works for relations just as well as it works for program-oriented data types. And I'm going to use a shorthand here to write 1, which means in the goal, it's the first premise that is appearing to the left of an implication. So in general, there might be as many premises of this kind as we want. Yeah? There was no previous theorem, was there? I don't understand the question. Right. So 1 here means the first premise of the theorem statement. In general, there will be a number of arrows, and the first premise is the thing to the left of the first arrow, the second premise is the thing to the left of the second arrow, and so on. So this is saying, let's do case analysis on what rule was used to prove this fact, the first premise. And that will just basically expand out the definition. Now we know the only state that satisfies that rule is the with accumulator state with these arguments, so that state gets plugged in place of the variable. Yeah?
Isn't the for all the same as the arrow though? So why didn't it just do destruct on the...
It's not the same as the arrow. And I'm not sure I want to go into that here. But since you've seen so much dependent type theory already, the arrow is for all where you don't mention the variable you've bound. And that's an unambiguous condition that tells you which is which. Yeah. Right. All right, so now we have this property. And what we can do here is just run algebraic simplification to use the definition we gave of fact invariant and compute using its defining equations. And now we get this not too scary looking fact trying to show that factorial of something equals factorial of something times 1. And this turns out to follow by ring for the same reason we saw last time, where we're using this theory of commutative semi-rings applied to the natural numbers, and we should be able to get any fact that follows from the axioms of that theory to be proved automatically using ring. So now we know that this is the invariant is compatible with our set of initial states. So that's step 1 of 3 to show this is a good invariant. The next one is to show that every time we take a step from one state to another, if the invariant held in the starting state, it also holds in the final state. So let us prove this as well. And it turns out to follow by a similar argument. So let me do a case analysis on our first assumption, which is about the step relation itself, standing for those arrows in that diagram. So let's see all the transitions we need to be ready for. We defined 2 arrows, so we should get 2 sub-goals here when I run this command. And indeed, yeah, that's a different kind of arrow. Two of these state transition arrows are over here. This arrow corresponds to the proof we just did about the initial states. Right, so here's the case where we started before where the accumulator was 0, where n was 0, and we just got rid of n and said, now we know the answer. Let me run simplification in each of these so we can see what we're working with. So we know that some quantity equals ac plus 0. We need to show that the same quantity equals ac. That doesn't look too hard. And for the other rule, we have that the factorial equals this expression, and we have to show that it equals this expression, which again doesn't look too hard. It's just modulo associativity and commutativity of times in the second case. So if I run intros to introduce names for our assumptions, in this case I can rewrite with our assumption h to use what we already know about the form of the factorial, and now we have to show ac plus 0 equals ac. Ring can make short work of that. And the same holds in the second case. We have an equation for a factorial. We want to prove another one. Let's rewrite with the equation we know to get this new form, which follows just from properties of arithmetic. Okay, so now we've shown this is really what we call an inductive invariant that continues holding throughout all the steps the system can take. The last thing we need, the property that makes this a useful invariant for this proof, is that whenever it holds of a final state, that final state actually has the correct answer in it. In particular, in any final state where the invariant holds, that state equals what we expected. It says that the answer is the original input. All right, so here is your chance to practice your skills of scientific induction. We've seen a few examples so far. What do we think is the right way to start this proof to establish that final states that satisfy the invariant actually store the correct answer? What argument should I pass to destruct?
1.
That's a good start. Yeah, let's see what happens. So now we're trying to show, given the invariant, we want to show that the ants field of the answer is constructor is really equal to the original input that we wanted. And if I run simple here, we'll get this invariant to be simplified down based on its definition. And we'll see what we know is, well, this will be easier to read with intros. We know that fact original input equals ants. We have to show this fact. Looks pretty similar. We've just wrapped an extra constructor around the two sides of the equality as well as reversing the order. We can run the congruence tactic, which is a general solver for goals that follow just from properties of equality. And this is one of those. We don't really need to know anything about these functions. We just need to know they are functions. And then that one is established too. All right, so now we know informally that this is a good invariant. We can finish convincing ourselves by actually using those properties to prove that the factorial state transition system always gives the right answer. So we can do that by saying, let's see, if we have any initial state and actually maybe I don't want to do that yet because I'm going to define something nicer for that below. All right, we'll do this in a more generic way than just proving it here. We've done the essential problem-specific work, and now let's formalize a more general idea of transition systems, of which this factorial system is one example, and prove some properties about those. So here I'm using Coq's facility for defining record types, which act a lot like records or structs or what have you in other languages. And so we're going to define a type of records. This is a polymorphic type, just like, say, the polymorphic list type in ML or Haskell. Its type parameter is some type of states, which is an arbitrary set. Given that, what we need to define a transition system are three things. We need a relation telling us which are the initial states, so that's a function from states to propositions, or a unary relation. We need a transition relation, step that goes from pairs of states to props, or in other words, it's a binary relation. And we need a relation that tells us which are the final states, which goes from single states to props again. And then I can define another kind of record that actually packages the state type up with the components that depend on it. So we say a transition system record contains a state set, as well as a transition system prime typed in terms of that set. And I'm writing a colon greater than instead of just a colon to declare an implicit coercion that will let us treat a transition system as a transition system prime in any context that wants the latter. So that will be convenient at times for working with these. All right, so process all those. And now here's an example of using this idea. Let's define a formal transition system for factorial using the components we just defined and verified. So it's actually parameterized in the original input. And the states are the states we defined above, and I just plug in this nested record the initial states, step, and final states relations. So now we have a first-class value standing for that picture, essentially. And we can use some generic definitions and lemmas to reason about it. For instance, here's one. This is a relation that captures which final states are reachable from a particular initial state. And let me draw this on the board in more traditional inference rule notation. So there are two rules here, and what they would correspond to is something like this. First, this relation, I'm going to write like this. It's a binary relation that connects two states, and it has a star superscript to indicate that it's the transitive reflexive closure of another relation. And I'm writing an identifier for the transition system over the arrow to indicate this is the relation specialized to that transition system. So if I left out the star, that would correspond to one step of the underlying transition system. With the star, we keep the steps of the underlying system and also add rules that make it reflexive and transitive, so you can take as many steps as you want, including 0. So the condition for this rule to let you take 0 steps, how are you allowed to decide you're done? You're done if the final relation of the underlying transition system says you're already at a final state. So then the appropriate thing to do is stop and do 0 steps into the state you already started in. Another rule says that if the underlying transition system goes from state S to S prime, and then we take 0 or more steps from that point, and we get to S double prime, then you can compose those together and get that. You can go from S to S double prime. So notice there are stars here and here, not here, which means this rule applies for cases of taking at least one step, where you step here and then take 0 or more steps here and then put those transition sequences together in order and get the overall transition. So this relation captures the idea of running from some initial state to some final state. The final state is the right-hand argument of the relation. Right, so here it is in Coq syntax. We see it matches what I've written there pretty closely. We mentioned the final relation here, we mentioned the step relation here, and final effectively acts like a function that is passed the transition system and extracts the final relation of that system. This is how we access the fields of records along the lines of the record definitions I gave earlier. And similarly, here we pull out the step relation of the transition system by calling the step function on it. Any questions about this definition? Yeah. It's not a keyword, it's just a name I chose. Yeah. It will, there'll be an example later where it's important. It's a little hard to explain quickly. It makes the typing work out. Yeah.
So for that, the final step, that's if there is the final state, then the case.
0 steps and declare that you're done. It's just to, this is, I'm feeling it might be better for me to dodge that question carefully. It's not interesting. It's just a way to give two views on the same type. One where the type of the thing tells you what sort of states it has, and the other where the sort of states is an encapsulated detail. And in some contexts you want one, and some you want the other. This is just a way of making them play together nicely. But that detail is unimportant for the main points I'm trying to make here. Question? Yeah. Yes, you can desugar it into sigma types as a primitive feature. Yeah, it's like a named nested sigma type. So I'm not sure for this crowd if that is a better or worse explanation than it's a record at this point. Yeah. Sure. All right, so we have this run from relation. I'm going to define one more derived relation that finishes the picture. It captures the idea of a complete execution of the system, where we have to start in an initial state. So this one is parameterized on a transition system and a final state, sorry. And what we say is there exists some initial state, st0, such that if we run from st0, we get to the result st. Therefore, that means st is a reachable final state. So this is the relation capturing for a transition system which final states could we actually reach in practice. All right, so are there any more questions before we prove our first theorem about these definitions? Okay, a good thing to prove would be that the states reachable via these relations are actually all final states. It seems pretty obvious, right? Because here's the base case of our recursion that requires you're at a final state. But it can't hurt to prove it. And here we start seeing some of the more interesting things we can do with Emacs breaking. Just a second. Sorry, does someone have a way to fix it?
Control L tends to fix it.
Oof. All right, thanks. So these rules we can see as just defining a type of trees. It's just another data type from programming. We love data types. There's nothing to be scared of here. And so we can do case analysis on these things, but we can also do induction on these things. And I showed you the general rule for turning one of these definitions for data types into an induction principle, and we can apply the same rule here. So what we're going to do, we're going to be showing that for all pairs of states, if the first one steps to the second one, then some predicate holds, and it's a predicate of the initial state and the final state. Our general induction principle will let us prove theorems of this form. This is really just normal structural induction, but extended in a small way to apply to these relations that we're defining instead of regular data types. So what we'll do then is we'll kind of cross out the conclusions of these rules. So I'm changing this into, from a set of rules you're allowed to use to conclude these facts, into rules that capture what are the obligations on you, the person writing the proof, if you'd like to use structural induction on these proofs. So instead of concluding that certain steps are possible, you'll need to show that the predicate you're proving holds of certain pairs of states. And we also find all the instances where we mention the same predicate recursively and we add a new premise where we are allowed to assume that the predicate we're proving holds of the arguments to the relation. So this is the induction principle. To show this fact, you must prove that each of these two rules is valid. And for instance, in showing that the predicate holds of a pair like this, you're allowed to assume it holds of a pair like this, and you also know these underlying facts about the step relations. So we can use this induction principle to establish this pretty tame fact saying that run from only targets states that are final. In particular, I can write induction 1, just say induction on basically induction on the proof tree that we use to establish this first run from fact. So we should get 2 sub-goals because there are 2 rules there for obligations. Okay, this first one looks okay. We know ST is final. However, are we going to show that ST is final? Well, there's a helpful tactic called assumption I think we saw already, which will prove this for us. And it's going to do this one too. This is a pretty basic proof. We already know what we need to prove, so assumption handles this for us. Okay, so what we showed is any state that run from can take us to is actually a final state, which is pretty obvious given the rules over there, but it's good to be able to prove it. So again, what we did here was essentially structural induction on the tree structure of one of these proof trees built up out of these rules. And that's one of the most important general proof principles for this kind of meta theory. Yeah?
I might have missed something up there, but what's the difference between assumption and apply?
Did we do apply already?
Oh, if we didn't, I apologize.
I don't think we did.
Okay.
Apply is more general. That's the advanced answer. Was there a question over there? No? Okay. And then it's an easy task to lift that result to our run relation, which remember tells us which final states are reachable from initial states. Or in other words, which answers will this algorithm give us? We'd like to show all these states we get to there are final. And I think maybe now we do want to use apply. Let me see what I want to do here. Actually not. Let's just do a case analysis on how we prove this run fact. And there's just one rule that says you start from an initial state and you run from there, like so. So we have a init for some state st0, which is able to get to st. And now we want to use the theorem we just proved, and now we want to apply. So apply is a rule for, let me just remember the name of this theorem, run from final. Apply is a tactic where you've already proved some lemma that will establish the fact you care about, and you'd like to use that lemma and change from proving the original goal to proving the premises of that lemma, which is a logically valid way to reduce the problem. I think this might not work. Yeah, so I'm going to use a tactic called e-apply, which is where we're going to figure out in the course of this proof what are some of the quantified variables that appear in the statement of run from final. In particular, notice this little question mark saying, to use that lemma, I'll need to prove a fact of this form, where the first and third arguments are exactly these two. But we may choose any second argument we want. That's what the question mark stands for. It's a unification variable whose value we will determine in the course of the proof. So we can call a tactic called e-assumption. In general, the e's you can think of as standing for existential, whether it's some other existentially quantified things you'll figure out in the course of the proof. You call e-assumption, which will figure out that this assumption does the trick when we set st equal to st0. All right, so now we have proved that any run of a transition system really ends in a final state. And one of the last ingredients to finally do our proof that the factorial system is correct is to characterize formally what is an invariant. And I'll do this with another inductive definition that's parameterized over the transition system, and also a relation inv for invariant that is a sort of a unary relation over the states of that transition system. We write state applied to TS to get the type of states that this transition system uses. And is invariant is a rule with two premises. To conclude is invariant, we need to show first, any initial state satisfies the invariant. And second, whenever you can take a step from st to st prime, if the original state satisfies the invariant, the new state does also. So these should look familiar from the properties we proved for the particular factorial system earlier in this file. But this is the completely general definition of an invariant that we will use in some of these generic results about state machines. All right, so we'd like to be able to show that if we have an invariant and we do a run of the system, then we indeed wind up in a state that satisfies the invariant. So, any suggestions how we should prove this? We've seen all the machinery that we need for this in the earlier examples. Yeah?
Destructive is invariant.
That's probably a good starting point. Let's basically expand out the definition of an invariant. So we'll get some hypotheses explicitly for the two facts that we have about what makes a good invariant. All right, that's a good first step. What's a good thing to do next? Intros, we could do that. Let's see. So we could also use induction. It turns out run is a predicate that's not defined recursively, so induction isn't super useful. It corresponds, it gives us the same power as case analysis. So case analysis is, I think, what we want to do on the proof of run. And I'll do that with another destruct on one. And we can even, let's see, is this going to work? Yeah, we can do them both at once. And so now we've expanded the definition of run into remembering, into telling us we have an initial state and it gets to the final state. All right, so let's make this all fit on the screen somehow. Almost. So here's our goal. Any ideas for a good next step? Yes, we'd like to do induction on the proofs of run from. And I'm actually going to separate that out into a separate lemma instead of just running induction here, though it's not strictly necessary. It'll be a lemma statement that looks much like this one, but I'll write run from instead. Let's see. Like so. And I'm going to copy these two conditions down here and write those in place of is invariant. Just makes this a little simpler to read. Delete that. And then, let's see, for this to be a true theorem, there's one more thing we'll need to know. Also, I'll call it a lemma and put a prime at the end. But to make this a true theorem statement, there's one more change we'll have to make. Any ideas what that would be? Actually, I'm going to remove this part suggestively. I think that, and then we want to add one more thing in place of it. I'll keep that arrow there, or maybe I won't. I'll put something later. Yes, the invariant is happy with. Well, I wrote something funny here too. Didn't mean that. The invariant accepts the first state. So if you're in a state that satisfies the invariant, you run to some other state, then the new state satisfies the invariant as well. And we're basically just going to use this hypothesis to conclude that. Something funny is happening here. This is one of the downsides of using the coercion mechanism that I vaguely explained at some point. You have to write more type annotations sometimes, but now it's happy. So for any transition system, if you make some 0 or more step transition, if the invariant held at first, then it holds at the end. Yeah?
Are we proving invariant the final time through invariant time?
Yeah. This is just a case of strengthening the induction hypothesis by proving it as a lemma, which is usually the nicest way to do that, instead of writing all sorts of stuff in line in the proof. So here we can do induction on 2, which is going to be the second hypothesis, the run from. Oops. Another fun fact, we need to write even more stuff here to emphasize inv is a prop valued function instead of a set valued function, otherwise things get confused. Now we should be able to do induction on run from. First goal doesn't look too bad. Let's just run intros in all the cases too. So in the case where we take 0 steps, we're done because the final and starting states are the same. We knew that the invariant held at the beginning, so it holds now too. And in this case, we are getting closer. So the key ingredients here that make this true, I think, are H, IH run from, which is our induction hypothesis, whereas H is one of our original assumptions in the lemma statement, and H2. And I guess H0 matters also. So how can we put those together to prove this goal? So we can run something called auto, which would, maybe E-auto, which would do this, but just for pedagogical purposes, let's first try to prove this more manually. We can apply our induction hypothesis, which establishes precisely the fact we're interested in, but requires us to show another one. So let's switch to showing inv st prime instead of inv st double prime. Now we need to show inv st prime. How can we do that? Yeah, now we can use H, which knows how to do that, given that, I'll use the E-apply variant, which works when we're not quite sure what all these quantified variables are, but we'll figure out in the course of doing the proof. Now we need a step fact. We happen to have one in the context, so I'll say use an assumption for that. Now we need to know that the invariant holds of st, and that happens to be exactly one of our assumptions. So that one's proved. And it was suggested to use a nice piece of calc automation, which we can do too. And instead of this manual derivation, we can make the computer do the work for us and just type E-auto to basically search all ways of applying the hypotheses that we have up to, by default, a depth of 5 for the proof trees, and you can increase that depth if you'd like more. Yeah?
So those variables with the question marks in front of them are like special variables that aren't like the other variables in the context?
Right, they're unification variables, where you choose one value for them by the end of the proof instead of making your proof apply to any possible value they might take. Yeah?
So I guess I missed where you used your lemma.
This is the lemma.
What's that?
This is the lemma. We haven't used it yet. Yeah. And so it turns out we can even make E-auto do this whole proof for us. Because it turns out, as these things go, this is a pretty tame proof, which is easy to automate. All right, so now we can use the lemma. Let's E-apply invariant final prime to prove a number of things, including this one. Happens to be exactly the assumption that destruct produced for us. And we need to show some run from, and we can say E assumption there, and we need to know that we have an initial state, we need to know it satisfies the invariant. Well, what do you know? Lurking just off the top of the screen is a helpful fact saying that any initial state satisfies the invariant, so let's apply that fact, and then our assumption gives it away. This one too, this derivation can be done with E-auto by adding a using clause that says include this lemma among the proof strategies that you consider. And then do I need to increase this? Maybe not. So what's the problem here? Oh, right. Yeah, this one's a little too fancy to use in that way because it concludes a generic quantified relation. It doesn't apply to a single fixed invariant. It applies to a different one depending on the context, and E-auto isn't quite smart enough for that. So we'll have to be satisfied with E-apply, semicolon, E-auto. And now we have established this key fact. So this is the main theorem of the theory of state machine correctness, saying if you have an invariant, then it's always going to hold of any state that the machine can reach. And now we can finally use that to prove that factorial is correct. Yeah?
So when you're doing a proof yourself, for example, when you're applying it, is there a way to like specifically state which assumption you're using, or do you just typically just write assumptions?
There is a way to state it explicitly. I'm not sure that that's the most useful thing because, especially if you just use assumption, if you happen to have two assumptions proving the same thing, it doesn't matter which one you choose. Because we're in proof land, which is generally regarded as proof irrelevant. Any two proofs of the same fact are equally satisfactory. All right, so let's prove the factorial is correct. In particular, If we run our factorial state machine to some state, which has to be a final state by the definition of that relation over there, then that state actually is the one we expected. So one way to do this is to use that theorem we just proved, invariant final, and I'm going to use a version of apply that actually moves in the forward direction instead of the backwards direction. We can apply it in one of our hypotheses instead of applying it in our conclusion. I might need to use e-apply here. Yeah, so because not all the variables will be obvious from the form of h, we need to use e-apply. Now we have that, and right. Actually, here, I'm going to use a different form of this, a command called assert, which says our invariant was which one? Let me just go back and grab the name of our invariant here. Fact invariant. Our factorial invariant must hold of ST. And we needed the original input too. So assert is a form where you state some fact that you think is going to be useful, and you sort of pause your proof, prove this fact, and then afterwards it appears in your context as one that you're allowed to use. So one way to prove this should be to use the general fact that we just proved. Let me page up and get its name again. Invariant final should help us prove this. So the first thing we need to prove is that this is an invariant, which we can do. I'm going to use a tactic called constructor, which applies for an inductive relation and just picks the first one of its defining constructors that actually applies to this goal and works the same as directly applying that constructor. So the first thing we need to prove is that any initial state satisfies the invariant. And this we've already shown somehow. I'm just going to page up and get the name of it. We proved fact invariant init, fact invariant preserve, and fact invariant final. Okay, we're going to use all these here. So coincidentally, we happen to have proved all these already. I guess we don't need the final part yet. Okay. Now we need to know that we can actually run to the state that we're concerned with. That happens to be one of our assumptions. And finally, now we know that the invariant holds. Let's use the fact we proved before, showing that all final states contain the correct answer. We can use a constructor here, or do we want that? No. So here we use, remember, one of the first things we proved was that run only produces final states. So what did I do here? Oh, it's not quite ready for that. Let's apply run final in H. And now assumption. And then this one is assumption 2. All right, so that establishes that any state that the factorial machine can reach actually is an answer is state that contains the correct factorial.
You go back to right before you apply the first assumption.
Here?
No, sorry,
The last line.
the last 2 lines.
Okay.
Yeah. You didn't have that explicitly.
Right. If I simplify in H, then it reduces to this. So assumption works modulo simplification. There are others. But the E versions in general will work in cases where to match the assumption or the lemma that you're using, you have to figure out the values of some of its quantified variables. But you're not sure what are the right values to plug in. So you leave placeholders to be determined later that you'll fill in when you actually know what are the right ways to instantiate the quantifiers. So for instance, this one didn't even need the E version, but this one I think did. This one didn't either. This one, remember one of these did. No, Okay, so this proof is too simple to actually need any of that machinery. But in general, you might need to apply a rule when you don't know what are the right instantiations of the quantifiers, and the E versions let you postpone those decisions until later.
Does the E standing for exist?
Yeah, exists or existential is how I think about it. All right, so finally we've proved that this factorial state machine always gives correct answers, and we did it in a way where we didn't have to do any induction that was specific to factorial. All the induction was factored away into a separate theory of state machines. Any more questions about the stuff up to this point before I do another example? Yeah.
So E assumption was the thing that filled in what those question mark variables should be.
Yeah.
But so when we used E assumption, we didn't specify what that variable should be. So is that something where, again, it looked into the concept and then found something that would work if you instantiated that thing to something?
Exactly. It does, E assumption does unification to find a hypothesis that can match if we make the right choices about the values of the question mark variables.
And so that, could that sometimes be wrong, unlike assumption?
Yes.
Okay.
So be careful.
So, yeah, so in what way will that be wrong?
There could be multiple assumptions that state different things, and it could pick the wrong one, and therefore assign the question mark variables in a way that makes a later stage of the proof impossible, while a correct choice would have let you finish the proof.
So can you then explicitly unionize or?
You can. I'm not going to. Well, you could write apply with the name of the hypothesis that you actually want, and that would be one way to do it. Yeah.
Why do you need to write proof?
Mm.
Like PROON. I mean, you can run with a waiting proof. So why wait it?
Just for readability.
Okay.
All right. So now I want to do another more interesting example, which is starting to get up to the point just barely where you might actually want to verify a program because it wasn't obvious that it was correct. And I'm going to do a simple example of a concurrent program, and we're going to prove that it always gives the right answer regardless of the execution order that a scheduler might pick between threads. So I'll write some pseudocode for this program, and then we'll look at the formalization as a state machine separately. It's some code that assumes there's a one shared lock across all the threads in your program. You can call a function lock to block until you're able to claim that lock for yourself. And then read some global variable, which is going to be a counter storing a natural number, into a local variable of your own, and then assign the global variable the value that is 1 greater than what you read in the local variable, and then unlock. So if you ran this code in a normal multi-threading system without the lock and unlock, you had 2 threads running this, you might actually wind up where the final value of global is just 1 because each of the threads runs this line before either of them has run this line, and you get so-called race condition, and you don't get the value you might expect where you don't know what order the threads are going to run in, but the combined effect of the 2 is to, say, move the value of global from 0 to 2 instead of 0 to 1, which is one of the undesirable behaviors you might get without synchronization in this program. So we can formalize this program as a state machine, which I'll do down here. It has a set of states, which you can also see in the Coq code up there, but let me explain what they are. Basically, the states correspond to lines of code in this program. So the starting state is a lock state, meaning the program is about to lock, about to take the lock. And when the program does actually manage to take the lock, then you get into the read state, which is this line. And then you can take a step over to write n, which is what you get when the program manages to read that global equals n. So this is we're basically encoding the values of local variables that the program still needs as arguments to constructors here. And the only case this shows up is to run this write command, we're going to need to know the value of the local variable. So whenever we read some global value n, we stash it inside this state value here to record what we just read so we can use it to do the correct write on the next step. And the next state after that, when we do the write, what this write does is it sets the global variable to n plus 1. And now we're ready to unlock. And after we do that, we will be done. You release the lock, and let's say we start there. So here's our state machine. It's pretty simple. There's this small finite set of states, except that the write state records what value we read in the previous state so that we can use that to write the same thing to memory. And putting that in there is what allows for us to have a race condition if we got the synchronization wrong, where the stored value within the write state might not actually agree with the current memory if some other thread is running and changing the value of the shared global counter. Any questions about what this example means? Yeah. I haven't said what we're proving yet. I'm just trying to define this as an unambiguous program whose behavior we understand as a state machine. All right, so Coq will accept this definition of a program. We also need to define what is the state of this program. This record is just defining the state that will be shared across threads. We have a Boolean that tells us whether the lock is held, and we have this global counter, which is a natural number. And then the full state, from the point of view of one thread, is going to be a pair of the shared state and the local state. And the local state is just one of these program state values. And I'm writing %type here to get the parsing to work properly. So this star is interpreted as a Cartesian product instead of a multiplication over the natural numbers. So this is the state that that one thread of the system sees. And now we define the normal components we need for a state machine. So first, what are the initial states? An initial state is where the lock is not held, the global variable is 0, and the program counter of the thread is lock, or the first line of that program. And a step, well, there are a number of different steps we could take. If we start out in the lock state, we're going to step to the read state, where before the lock had better not be held, and afterward it is held, and the global has been left alone. And then we can take a step from read to write of G, where we just copy the current value of the global variable into this write constructor. And a write action replaces the global variable from the before state with one higher than the value that was saved inside the write node, and transitions to the unlock program counter. And finally, we can move from unlock to done by replacing the current lock state with false to indicate we've released the lock and not changing anything else. So this is basically a formalization of the picture that I drew over there as yet another inductive relation in Coq. Yeah?
Why is lock sort of free in most of the states? Like it could be anything.
Because those transitions don't touch the lock, so they'll work no matter what the value of lock is, and they won't change it. We expect the program is only running when the lock is held at these points. But just to allow more opportunities for bugs, so it's a more interesting theorem to prove, I'll put this in here. All right, and to finish off this three-part definition, the final states are exactly those where let's not constrain the global state, but the thread itself must be done. It must have reached the end of the sequence of instructions. All right. Any other questions about what this formulation of the program means? Yeah.
So some domain kind of multi-threading, but you're not locking that yet.
Right, that's not here yet. It'll be coming up soon. All right, so we can package this in a state machine, like before. And let's not prove anything about this directly. I'm going to define next a generic operation for composing two state machines in parallel. Yeah?
Just for your initial state, why did we start with global being 0?
Because I felt like it. The theorem I'm going to want to prove is that global is 2 after 2 threads have finished running. So that gives us a simple theorem statement to aim for. All right, so here is a generic operation for a generic initialization step and final state relation that will work for programs in a certain style. It's polymorphic in a type of shared states and 2 different types of private states. And think of the private states as corresponding to the states in a picture like that one for 2 different threads. We have an initial state relation for each of 2 state machines, where the state of the first combines the shared state with one kind of private state, and the state of the second combines the shared state with another kind of private state. So a state of the combined machine is initial basically if the initial relations of each of the sub-machines accept it, where each of these relations is being passed the shared state as well as one of the 2 kinds of private state. So we have a triple, the state of the combined machine is a triple of shared private 1 and private 2. And we pass shared and private 1 to the first relation and shared and private 2 to the second one. And similarly, we have the steps that the composed machine can take. There are 2 rules. One where we pull out the first and second components of the state and have the first machine take a step and then drop those components back into the appropriate positions down here. And another where we pull out the first and third components, put those together and have them take a step in the second machine and then drop the results back in. And then we can similarly characterize what a final state looks like. It's basically the same recipe as for initial states. So we can put all these together into one parallel state machine. It's a generic operation to compose together any 2 state machines that split their state into shared and private parts. And if you have 2 state machines that agree on what is the shared state, you can compose them together in this way, and you get basic interleaving concurrency. For instance, we can, now that we've put all those verbose definitions in place, we can do this simple definition of the parallel composition of 2 different versions of that thread. So 2 increment operations running in parallel, just by passing the increment state machine as both arguments to the parallel function that we just defined. What we'd like to show is that in any run of this system, when it finishes, the lock is unheld, the global variable has gone up from 0 to 2, and both of the threads are in the done state. Yeah, so this is the end of the template code that I have. So what I wanted to do for our last 20 minutes or so is to try to basically come up with a good invariant that we can use to prove this. Yeah?
So the type of parallel applies to all of its arguments to the transition system? Is that right?
Yes, the type of this variable is a transition system,
Okay.
which makes it a legal argument to run over here. Yeah?
You said that the 2 transition systems need to agree on what the shared state is. Where is that shown in the code?
The fact that we have these 2 transition system prime arguments that you mentioned the same variable shared in their state types. And they have potentially different variables for the private state parts, though we actually make those the same as well when we apply it specifically at this point. Yeah?
Was there somewhere where you'd already guaranteed that both threads didn't have access to the lock at the same time? Or is that something
That's something we need to prove.
still
Well, let's see. The semantics of the lock says you can only take a lock transition if the lock is unheld at that point. So maybe
So where is that? Is that specified already somewhere?
that was in the step relation for the single thread, which said the lock transition starts in a lock false state and steps to a lock true state. Yeah, if this was just some arbitrary value, then the theorem would not actually be true. So we're assuming a correct implementation of locks there. All right, so any thoughts about what invariant shows why this is a correct algorithm? Yeah.
Maybe you could prove something along the line of both threads are never going to be in the read or write state at the same time.
Mhm. So, okay, what do you mean by the lock invariant?
That if there's only one,
Oh, I see. You were giving a name to the property he described.
like if there's only one system.
Yeah. That is one of the properties we will want. So, here's a useful function to have. We can write a function from, let's see, what did we call the state of a single thread? It's a increment program. We can write a function from an increment program that tells us whether we expect that it has the lock at that point. And this is a useful thing to do. So if you're at the lock state, then you think this thread is not supposed to have the lock yet. And if you're at the done state, the thread should also not have the lock. Otherwise, we think that the thread does have the lock. So then we can write something like programs agree that takes in two programs, returns a proposition, and it will say something like, actually let me write it this way. It's a predicate that tells us whether one program is okay, given also the state of the other program. And there will be a few cases we want in here. So if we're in the lock state, then we don't have any requirements. This is always true. And if we're in the done state, similar situation. But if we're in the read state, then so self stands for basically the program counter of one particular thread. Other tells us the program counter of the other thread. If we're in a read state, what do we want to require of the other thread? Right, we want to say has lock of other equals false. And similarly for write, we want to say has lock of other equals false. And there's one other thing we might want in here, which is we'd like to know that this write value, the number stored inside write is a correct one. And one way to do that is to say, let's have the value of global be another parameter here. We better get that the value stored inside write is actually the current value of the global variable. And what's left? We have unlock. We might as well say that we expect the other thread does not have the lock at that point. So we can start writing an invariant that will take in, goes from a state of increment to TS to a prop.
Doesn't that mean that if one was trying to take the lock, the other one couldn't have the lock right away? Don't you want one to be waiting in the unlock state while the other one has the lock? We wrote when this one is unlocked, the other one should not have the lock.
So unlock is the state for waiting to unlock.
Yeah.
Done is where you go after you finish unlocking.
Right, but so you should be waiting in the unlocked state when the other one has the lock, right? So it should be okay for the other one to have the lock here, right?
The way this program is set up, when you get to unlock, you're supposed to be the holder of the lock, and you don't have to wait for anything.
Oh,
You immediately unlock it.
Okay, sorry.
Yeah.
Is there a reason I prefer, so you define has lock returning a boolean rather than like a proposition, and then you could have it be prop true and false, like you have to put the capital true?
There is, yeah. I'll show it in a moment. There's a good reason. Yeah. It's actually implied by the definition of has lock. It always holds when you're in the unlock state. So when does the invariant hold for a state, let's say global equals G, locked equals L, and PR1, PR2, when program OK G, PR1, PR2, and likewise the other way around. For all GL, PR1, PR2. Okay, so this is a starting point, but it's not quite strong enough. Any ideas what would be an important property that this invariant is not capturing that we actually need here? G is not changing. We want G to change to the right answer. So the invariant holds in one state of the program. It doesn't have to capture evolutions over time. So the fact that G is always the same in the different parts of this doesn't tell us immediately this is a bad invariant. But is there another idea somewhere? Yeah.
That means you want to done global.
We need to somehow capture the protocol for incrementing global so that we know that when we get to the end it has the right value. Yeah, so what would be a good way of doing that? So here's a hint. We can actually write this without variables for G and L. Those values are implied by PR1 and PR2. And if we capture that implication, then we get to an invariant that works. There are probably other ways to do it also, but this is the way that I found. For instance, let me show you how we can get L. I'll give it its own line also. The value of L is exactly, it's true when one or the other of the program threads has the lock. So this is an example. This is showing why it's useful to use Booleans there instead of props. So you can compute the lock as a function of the program counters. And we can actually do the same thing for this shared global variable. And the code for it looks pretty similar to this, but with a different infix operator. Any ideas how we can compute the right value of the global variable given effectively the program counters of the two threads? Let's make some auxiliary definitions in any cases we'd like to use match, and then reference those auxiliary definitions in the invariant. I think that'll make it easier to read. Do you have a particular auxiliary definition in mind? But I'm trying to, I think we should write a generic function that is not specific to PR1.
I know, but
Okay.
I'm just saying how it works.
Got it. So what's the intuition for this function before we think about the code? Let me suggest an illustrative name, contribution from, that takes a program as an argument. What do we call this thing? It's a increment program. And it returns a nat. Now we do a match. And what are we looking for? And how do we use the match results to get an answer? Sorry? Which one of these states do you mean? You're saying we want to match the right state? And what do we return? And so there's no end scope here. So right is actually the program counter just before the write happens. So I think we don't quite want to give a contribution of 1 here. It's actually the state right after the write happens, whose arrow is labeled set global equal to n+1. The unlock state is the first one after we've truly done a write. So what I think we want to say is, if the program counter of this thread is unlock, it has added 1 to the value of the counter so far. And similarly, if the thread is already done, it has added 1 to the value of the counter. In any other state, we expect it has not yet added anything to the value of the counter. So we have this contribution from, and we can just add together the contributions of the two threads. And the way I've written this, we'd have to kind of copy this over, which is why it might be nicer to bind a variable to that, but I'll leave it like this for now.
So this feels like double
Double counting? What do you mean? I don't understand yet.
I think it captures the contribution of the program across its entire execution. So it's like it hasn't contributed anything until lock, and then from lock, and then.
Actually, I've just remembered how we can leave out this global parameter here. We can compute it from the program counter of the other one. It's just the, here, I'll reverse the order of these. The value we're storing there should be exactly the contribution from the other thread. So now this program OK is simpler, and that's why I didn't remember having to copy this before. All right, so here's our full invariant. Each of the programs is OK with respect to the other one, and the shared state can be computed from the private states of the two threads. Yeah?
Maybe I missed this. How do we know that the two threads both have the lock at the same time? So then we assert that
That's in here.
one or the other has the lock.
It's in program OK. Read, write, and unlock are exactly the states where we consider that this thread has the lock, and we require the other one does not have the lock when we're in those states. All right. Sure.
So when you have program OK, PR1, PR2, and program OK, PR2, PR1, what is the intuition behind those two? Is that to kind of capture both possibilities of the program?
The way, so for instance, program OK makes sure that its first argument, if it's a right state, is storing the correct value. So we need to use it with both argument orders to constrain both of the states to be storing the correct value. So you can sort of read this as PR1 is OK with respect to PR2, and it's not a completely symmetrical notion, so we have to do it both ways. Yeah?
In your pattern scheme, is there a way to do like this pattern or that pattern in one log instead of two different logs?
I don't remember. So maybe we can do this. Okay. All right, so, yeah.
Where was it specified that the global starts at 0?
In the initial relation for the single thread, global starts at 0, locked starts as false. So I think in the interest of time at this point, I'll switch to another buffer where I have the proof already filled in for this invariant, and we can just see how this finishes up. Let's see. The statement of the invariant here, pretty much the same, except I've defined a separate function shared from private that combines together the two steps that we did up there. Oops. So shared from private is a function that, given the states of the two programs, computes what global state we expect at that point. And here's the same instruction OK that we just wrote there, possibly in a slightly different order. And here's the invariant statement. Instruction OK, this is what I wrote as program OK. Had better hold for both argument orders, and therefore the invariant will then hold if we've built the shared state using this recipe for getting it from the private state. And I prove one extra lemma that restates that invariant definition in terms of equality, which makes the proof a little easier. And we showed that any final state of the combined system, given that invariant, actually has the form we expect. Where the lock is not held, the global is 2, and both threads are done. And you can read the details of this proof offline. I'll just mention that inversion is a useful, very important tactic which works like destruct, except you should use it whenever at least one of the arguments to a predicate is not a variable. It applies fancier logic to rule out some of these rules of a judgment system as inapplicable because of the structure of one of the arguments to the predicate. So that is important to use, again, whenever one of the arguments to the predicate is not a variable and therefore might be somehow impossible for some rule to generate. So then we can prove that in any run of this system we get to the state we expected, where the global counter really stores the value 2. And yeah, I'll leave the details of this proof script for offline inspection. We do a bunch of inversion and destructing. Subst is a tactic. Let me just show you what this does. When I run inversion directly, I get a bunch of these extra equalities, like the variable PR1 turned out to equal lock, and the variable SH turned out to equal this particular state. Subst is going to find all the equalities over variables, and it will eliminate those variables by replacing them with the things they're equated to. So every place we see PR1, like here, we'll see lock instead after I run subst. So H0 will, this PR1 will change to saying lock, and this SH will change to saying this. Like that. And so we just do inversion on appropriate parts. Change is another useful tactic to find all occurrences of this term, replace them with this term. When calc is able to prove that those two are equal in a particularly simple way, just by applying the definitions of recursive functions and so on. So we do that, and then we apply our definition of the invariant, and we do a case analysis on which step we take. This is the key part of the proof that shows that one step preserves the invariant. And then there's these long tactic chains here, which do things just the right way to get this to work, where we do case analysis on one program and then inversion on a step that the other program is taking. So now we're considering a sort of a cross-product set of cases, all the values one program might have and all the steps another program might take. And we want to show all these combinations preserve the invariant. We do appropriate inversions to make that work, including inversion on the structure of the invariant. And then we simplify everywhere. We do propositional simplification, and we get some tactics that understand the theory of equality to do the rest. And we apply the mirror image over here, where we're doing a case analysis on the first program instead of the second one. And then that establishes that this program is correct. So this is showing that for all possible interleavings of this state machine, increment 2 TS, when we get to a final state, the program really looks like this. It's a uniquely determined state, so there's no non-determinism at the level of full executions of the program. Yeah?
What would the OR combination do then?
The OR combinator tries one tactic, and if it fails, it tries the other one instead. Yeah?
In terms of proof holistically and cost, if you were proving this monolithic property of both mutual exclusion and like end states afterwards, are there tools and costs on how to split these two things up? Like say the lock gives a mutual exclusion and I want the global state, combine them somehow in a program to try?
You can definitely do that. The details,
The way this is actually done in a bigger program.
there are so many different ways of doing that, including systems that are called program logics that build in rules, general rules like that, and let you apply them to prove specific properties about programs. I don't think I have any details ready to give in this setting, but if you want to look at concurrent program logics online, you'll see examples that I think address your question. Yeah.
So we sort of like got everything right here, and we're just our invariant was right. But like we define this transition system, so is there a really easy way to just take it and say, okay, give me possible traces of the system, which is not deterministic, like multiple different interleavings?
If you want to get one interleaving, that's easy enough to do using eauto. If you want to get many of them, the built-in tactics aren't really oriented towards doing that.
So you sort of have to manually.
But you see that all like all from 8.55 to
I don't know. I haven't heard of that feature before.
okay.
Yeah.
So we're proving this whole program correct, right, in a multi-term system. What are the things we're trusting here? I'm guessing, so we're like trusting that we transcribe the program correctly, and we set up the initial states correctly, and our like has-lock definition has got to be correct. So it seems like there's certain things we prove, but then there's also there's this like gap between what the code is and what we like put
Yeah.
into talk.
I'd say in general, we need to convince ourselves informally that the state machine we've written down here is the one we intended to prove theorems about. Almost everything else is untrusted.
Okay. So the transcribing of the state machine, we have to like just look at that with human eyes.
Yeah. You could prove additional theorems just to increase your confidence that you got the right one. If all the properties check the properties you expect actually hold of it.
Is there some way to like, I mean, isn't there like, you can extract like OCaml or something, like actual runtime code, and then would that give you something closer to like, I guess you still need to like human verify that your big machine is correct in that case. That shouldn't get you anything closer. Okay.
Right.
What is extracted?
Nothing gets extracted here. I haven't used extraction here.
Do the extraction like he was talking about the OCaml and Haskell. Is it not the theorem, just maybe the definition of the function?
Yeah.
That's what gets extracted.
Right.
And then you have the confidence that the theorems back it up.
Right. In general, I'm not talking about extraction in these lectures, but it's an interesting feature of Coq that many developments use. So implicit in this formulation of the program as a state machine is the idea that every instruction runs atomically. Every step happens atomically. That's implicit in this formulation. You could formulate it differently and break some of these steps into more atomic steps that allow for more potential mistakes, which is always fun. Yeah. Right. Yeah, it's not a supertype for an interesting reason. I think the best answer is look at the code, and it might make sense why I did it that way. The definitions the definition of parallel composition would not have type checked if I didn't decompose it that way. And just looking at the code, I think would explain why. Okay, thank you.